Hello, ladies and gentlemen. The oil-producing company Gazpromneft and the service company GeoSplit, which provides dynamic marker-based production logging technology services, are presenting the case study of the project, increasing the accuracy of production allocation from each reservoir, integrating TAML-1 well construction technology and the dynamic quantum PLT method in the field NP. The main problems of the field NP development are the significant residual reserves and the complex geological structure. Oil reservoirs, or reams, are located under massive gas caps, which make the reservoirs difficult to access. In addition, the underlying waterbeds are of great concern due to risks of water cut increase. Among other challenges are high vertical geological heterogeneity and multi-layered oil reservoirs with low permeability. The development of such complex fields requires new approaches to drilling, exploration, and field development, since conventional solutions are uneconomical due to the high cost of drilling technologies. In the current economic settings, such oil and gas production is not economically feasible. The new custom solution was developed by the multidisciplinary team of the operator company. Multilateral TAML-1 completion using the rock properties in the reservoir top interval and a set of swell packers to create an isolated branching point. If a well penetrates more than one reservoir, production from each of them must be accounted for individually in accordance with the legislation. For these purposes, dynamic quantum production logging technology was selected, since it has no limitations with this well design, unlike conventional logging methods. The dynamic quantum production logging technology involves the use of quantum marker reporters, high-precision indicators of reservoir fluid inflow. A composite material with markers is placed into special downhole inserts installed in the lower completion of a multilateral well. The marked material is a plastic composite. It means marker tapes that release indicators into the reservoir fluid at a stable rate and duration. Different types of marker tapes, oleophilic and hydrophilic, are combined so that the markers are released exclusively into the target reservoir fluid phase, oil and water respectively. An individual marker code is responsible for providing data to evaluate the individual contribution of each lateral. After the liners with quantum marker inserts are run downhole, the latter are used then in subsequent production surveillance. Reservoir fluid is sampled from the wellhead and the samples are analyzed using a flow cytometry analytical complex. According to this method, dispersed media are analyzed on a particle-by-particle basis using light scattering signals. It helps identify the quantitative distribution of oil and water markers of each code with high accuracy. The data of long-term dynamic quantum production logging technology in a producing well, coupled with the analysis of the historical performance of the target well and the nearest neighbor wells, provides a basis for developing recommendations on how to optimize development of complex fields. Horizontal laterals of the well pierce a fault trap, bounded by two faults forming a structure in the shape of a step fault. The target layers are separated by impermeable interlayers predominantly composed of clay. Due to this, production can be accounted for separately for each lateral. Since the trajectory of the lower horizontal lateral passes near the oil-water contact, there are risks of water flooding during production. So the two downhole inserts with inflow tracers are placed into each lateral for purposes of surveillance. The upper lateral has the number 1, the lower lateral is number 2. During the entire time of surveillance, 8 surveys were conducted to obtain the distribution of the laterals contribution for each period. The data of dynamic quantum PLT and the field geological settings were analyzed and the following observations were concluded. Uneven performance of the laterals was observed in the first 3 months of surveillance with a predominant contribution of horizontal sidetrack 2, which is due to a non-steady fluid flow along reservoirs. A relatively uniform production starts from the next quarter, with a slight predominance of the contribution from horizontal lateral number 1. At the same time, water cut in the formation fluid is growing gradually during well operation. Absolute figures of the production dynamics reveal a significant discrepancy in the performance of the laterals in the initial months of production. Thus, a sharp drop in the fluid flow rate in January 2021 observed in the performance of lateral number 1 piercing the AB1 formation indicates the non-stationary nature of fluid flows in the drained area. The well performance historical data is also studied. The dynamics of reservoir performance, decreasing fluid flow rate and the bottom hole pressure indicates a clear depletion effect in the well drainage area. This conclusion is also confirmed by the starting pressure after a long well shutdown, which has significantly decreased from the initial one. The rapid increase in the gaze factor since the well restart after shutdown is characterized by a decreasing gaze oil contact level. As the contact level decreases, the gaze breaks through to the wells located closely to the gaze pool boundary. In this case, it is important to optimize the energy loss from the expansion of the gaze cap for the sake of cost-effective oil well operation. In addition to identifying the sidetrack performance distribution in the subject well for the purpose of split production accounting for 2 reservoirs with different porosity and permeability, data obtained using dynamic tracer-based production profile surveillance enables monitoring production indicators without well shutdown, as well as development recommendations for its optimization. In order to verify the dynamic quantum PLT method in the oil and gas condensate field NP, a comparison was made with the coupled sector model of reservoirs AB1 and AB2. This model was developed taking into account the basic geological settings and engineering factors and describes the real reservoir processes occurring in hydrocarbon deposits with the required accuracy. The simulation involved evaluating various options for adapting the model. Eventually, the option showing the best convergence of the model with the production history was selected. The comparison reveals a satisfactory correlation between the data obtained using dynamic quantum production logging technology and the reservoir model calculations. Deviations during the first several months are associated with a non-stable reservoir flow, which in turn correlates with the well reaching a steady-state production mode. In conclusion, there are several points to mention. The first one is that the Tamil-1 multilateral well in question was built for the first time in Russia based on a fundamentally new design, making this proposal feasible for further field development. The well was drilled with a 38% reduction in capital expenditures, CapEx, and construction time. The second is that novel inflow tracers were successfully implemented in this well. Its design enables separate production allocation without well shutdown and meets the requirements following legislative regulations. Inflow tracers application significantly reduces the cost of surveillance in complex well trajectories. Finally, it provides the opportunity to conduct production profiling on demand and update reservoir models for hydrocarbon recovery increase in the future. This concludes the presentation on the topic. Thank you for your attention.